Welcome back to day 11. Here's a trap that catches even experienced people building AI. You train a model, and it looks amazing. It gets basically everything right. You're thrilled. Then you show it new, real-world data, and it falls apart. What happened? You've hit one of the most important problems in all of machine learning. It's called overfitting. It's the difference between a model that truly understood the pattern and one that just memorized the answers. Today I'll show you exactly what that looks like. We'll literally watch a model overfit in front of us, and then measure it with real code. Let's dig in. Here's the whole idea in one line. Memorizing is not the same as understanding. Think about two students studying for an exam. One actually learns the concepts, so they can handle any new question. The other just memorizes the answers to last year's practice papers, word for word. In the practice test, they both look perfect. But on the real exam, with new questions, the one who truly understood does great, and the one who memorized falls apart. Overfitting is a model being that second student. It memorized the training data instead of learning the real pattern underneath. Let's be precise about it. Overfitting is when a model learns the training data too well, so well that it starts memorizing the specific examples instead of the general pattern. It even soaks up the random noise, the little quirks and errors that happen to be in that particular data. So it scores nearly perfectly on the data it trained on. But because it memorized quirks that don't apply anywhere else, it stumbles the moment it sees something new. It learned the examples by heart, but it never actually learned the lesson. Let me show you this happening. The blue dots are our training data. They roughly follow a nice, gentle wave, but they're a little scattered because real data always has noise. Watch the red line. That's our model trying to fit them. At first, it's a smooth, sensible curve. It captures the general trend. That's understanding. But now watch what happens as we let the model get more and more flexible. See it start to bend and contort, twisting itself into knots to pass exactly through every single training dot. It's obsessing over each point. And here's the tell. When the new orange test points appear, the wildly wiggly curve misses them badly. It memorized the blue dots and lost the plot entirely. That is overfitting right in front of you. So how do you catch overfitting in practice? You look for a very specific, telltale gap. An overfit model scores wonderfully on the data it trained on, but poorly on new data it's never seen. That gap between training performance and real-world performance is the smoking gun. And this is exactly why, in machine learning, you always hold back some data that the model never trains on, and you test it on that. If it's great on training but weak on the fresh test set, you've got overfitting. Training score alone can fool you completely. Let's prove it with numbers. Let's make overfitting undeniable by measuring it. We're going to take some noisy data and fit two models to it. The first is a simple, gentle curve, not much flexibility. The second is a super flexible, wiggly curve, the kind that can bend to hit every point, just like the animation. Then, and this is the important part, we'll test both on fresh data they never saw and compare their errors. If overfitting is real, the flexible one will look great on training, but terrible on the test. Let's look at the code. Here's the setup. We have 10 noisy training points, and a separate batch of fresh test points the model will never see while learning. Then we fit two curves. The number called deg, for degree, controls how wiggly the curve is allowed to be. Degree 3 is a simple, smooth curve. Degree 12 is wildly flexible. It can bend all over the place. For each, we measure two errors, how far off it is on the training data, and how far off it is on the new test data. Low error is good. Let's run it and compare. And there it is in cold, hard numbers. Look at the simple curve first. Its training error is tiny, and its test error is also small, about 0.03. It does well on both. It understood the trend. Now the flexible curve. Its training error is basically zero, absolutely perfect on the training data. Impressive, right? But look at its test error. 23. That's hundreds of times worse. It nailed every training point by memorizing them, and then completely fell apart on new data. That massive gap, near perfect on training, disastrous on test, is overfitting, measured. So burn this fingerprint into your memory. When a model has very low error on its training data, but high error on new data, that is overfitting almost every time. It's the single most useful diagnostic in machine learning. A model bragging about perfect training accuracy means nothing on its own. The real question is always, how does it do on data it has never seen? That's the only score that tells you if it truly learned or just memorized. The good news is, once you can spot overfitting, you can fight it. First, more data. The more examples you have, the harder it is to just memorize them all. The model is forced to find the real pattern. Second, use a simpler model. Fewer knobs means less room to contort and memorize. Third, always hold out a validation set, a chunk of data you check against during development, so you catch overfitting early. And fourth, a technique called regularization, which gently penalizes the model for being too complex, nudging it to stay smooth. Together, these keep a model honest, learning the lesson, not the answer key. Let's lock it in. Overfitting is when a model memorizes its training data, noise and all, instead of learning the real pattern, like a student who crammed the practice answers. The classic sign is a big gap, great on training, poor on new data, which is why you always test on data the model never saw. And you fight it with more data, simpler models, and holding out a validation set. Spotting overfitting is one of the most valuable skills in all of AI, and now it's in your toolkit. So that's overfitting, the crucial difference between a model that truly understands and one that just memorized the test, and you watched a curve tie itself in knots to prove it. That wraps up our tour of the core foundations of how machines learn. Tomorrow, we start pointing all of this at the technology behind ChatGPT and Claude. We're going to dig into large language models and how simply predicting the next word turns into something that feels remarkably intelligent. Thanks for building with me today. See you tomorrow.